The ones of you following my channel a little bit longer might remember this thing right here. It is the Stern-Gerlach experiment, or at least it is supposed to be the Stern-Gerlach experiment in the future. And no, I haven't forgotten about it, even though it has collected some dust.
If you don't know what the Stern-Gerlach experiment is, I recommend watching my other two videos about it. Especially in the first video, I explain the basic principle of the experiment and the setup in detail.
But just to refresh your memory a little bit, for those who already know, I'm trying to create a potassium atom beam at this side of the vacuum chamber. This is a KF40 tube. I have a turbomolecular pump down here, and I'm trying to create a potassium atom beam which flies through this tube and gets detected back here where currently this Inficon vacuum gauge is. There will be a detector to detect this atom beam. And later I will put two magnets in between or in the flight path of these atoms and try to deflect them depending on the spin of their electrons.
I am very sorry that I haven't made a video about this experiment for so long. But since I can't machine metal myself and some components have to be made out of metal, I have to rely on other people to do it for me. One of those people is Silver Oranges. He contacted me and offered to help. It is incredible that people all over the world are willing to give their time to help me with my project, and I'm incredibly grateful to them. After many months, the package arrived from the USA, and I can proudly say that the Stern-Gerlach experiment is now an international collaboration. In this package was an important component that I will talk about in today's video. And additionally, there were some PEEK and PPSU rods that I can certainly use for other projects. So thank you a lot to Silver Oranges.
And in today's video I'm going to talk with you about the atomic beam furnace. It's the part that creates the potassium atom beam which flies through this tube. And this is the awesome piece he machined for me, or the pieces. And I will explain to you what everything here is in a second. An atomic beam furnace is basically, there are different types, but the one I'm going to use is basically just a heated chamber with the element, in this case potassium, inside. And when the potassium gets heated in a ultra high vacuum or in a high vacuum, the potassium will vaporize, or atoms will vaporize. And of course, if they are in a vacuum, there's nothing to stop them from flying in one direction. So what this is, you can see that this is the main chamber, and here is a KF40 flange, and just imagine this is the vacuum chamber, and it's just going to attach just like this, and an O-ring of course is going in between those two parts. There are different ways to design an atomic beam furnace. The ones I found were pretty hard to machine, or were pretty complex, because they basically, all of their parts, the heating wire and everything, was inside the high vacuum. To make it simpler, I looked around and searched for simpler designs, and I found a paper where they described basically this design right here. I designed it in Fusion, but I ripped the idea from this paper. I will link it in the description down below. And you heat the chamber from the outside, and the only thing is exposed to the high vacuum is your element and the inside of this furnace. That makes the design way easier, and that's the way I chose. The first thing I have to do, as you can see, the centering ring is a little bit too large to fit in the machined groove right here. So the first thing I'm going to do is to widen this groove here to accept the centering ring for the O-ring. And as you can see, now the centering ring fits perfectly. And I messed up the surface here a little bit, but I'm going to polish it anyway, so that's not a problem. can see, the centering ring fits perfectly, and I can, without a problem, connect it to my vacuum system. You may now ask how this even works. The way this works is that a sample of potassium or any other element can be put in the middle hole right here. I have an additional piece, which is this one right here, and it can be screwed on top of this chamber here and seals it off. And as you can see, there is a hole in here, right there, where the potassium atoms can fly through when they get in the vapor phase inside the chamber here. The problem is this opening here is quite big, and I want a well-defined small beam of potassium atoms, and with this I would have a beam of, I don't know, half a centimeter wide, and that's not suitable for this experiment. So we need a small beam, and that's what these pieces here are for. I am using two M4 threaded rods, which can be screwed in this component right here. And they get locked by these nuts right here. I had to file them down so they would fit there. And then I have these two discs here, and they go on like this. And as you can see, they have a recess here inside the disc. And my plan is to use an optical slit for a spectrometer, which has you can buy different ones with different slit widths. And I'm planning on using, I think, a 100 micrometer slit, and this will be placed inside this recess here and be clamped down with the other disc. There are two nuts which go on this end here, just like that, and then the optical slit is in between these discs. This sits on top of the chamber, and all the atoms coming out of the chamber have to go through this slit, and by the slit they get their well-defined shape. I don't have the optical slit yet because it's around 90 bucks at Thor Labs, and I currently don't have the money to buy them, so I will wait and get them as soon as possible. The problem with this concept is that for an atom, this slit is huge. So what will happen is that if you imagine that this card here is the optical slit, and this is the slit inside, that atoms, they can't only fly through like this, what I want, you know, straight through. They can also go like this, so basically at all angles. And it's like shining a flashlight through here, and the beam will spread out after the slit. And that means I won't get you can see it on top of the desks right here, I think, a little bit. So the beam widens, and that's a problem because it didn't solve the initial problem of wanting to have a well-defined beam, and that's what this part here is for, in case you wondered. Let me just remove the two discs. Just like in an optical system, I have to collimate the beam of atoms. It's the same with a beam of photons. So if you imagine this is the slit, the atoms are supposed to only go straight towards the slit. So either way they fly through the slit or hit the walls on the side, but they are not allowed to go sideways because this way the beam widens after the slit. So what I'm going to do is use this part here as a collimator, and I'm going to use hypodermic needles, and I will cut them into an appropriate length so they can be stacked inside this area right here. And if you imagine, it's just like having a bunch of straws in front of this slit. The straws allow the atoms to fly only in one direction. If the atoms fly in another direction, they will hit the walls of the straw. So the next step is to cut a bunch of hypodermic needles to the right length and stack them inside this part right here.
Of course, while cutting the needles to length, my rotary tool broke down and I had to fix it.
I now have cut multiple of these hypodermic needles into length, but as you can see, by cutting them, the ends got quite mangled up. So I'm now going to sand them at both ends to get clean ends. I have now sanded down all the ends. I cleaned them with soapy water, acetone and isopropyl alcohol and dried them so they are ready to be put in the assembly. I have put some tape at the end here to keep the tubes from falling out again. I have now mounted all the cannula tubes inside the holder here, and as you can see, it created a lot of small channels where the potassium atoms can travel through. You can see it better if I hold a flashlight at the back. Another important thing to mention is that all these holes here are through holes, as you can see. And we also, or he also opened up these holes here. The reason is that you want to avoid having a closed up or semi-closed up space in your high vacuum chamber, because you're creating what's called a virtual leak. So basically, compared to the pressure and the density of air molecules inside a high vacuum, the amount of air molecules inside a hole, like for example this one right here, if there's a screw inside, is immense. So you will have a basically or virtually unlimited amount of air molecules which will slowly diffuse out of this hole here and steadily contaminate your vacuum, and you will never get down to a sufficient pressure. So you need a way for the air to escape, and that's why these here are through holes. And you may ask, what's with these holes right here? Because they obviously are not through holes. There will be a screw in there. And the way this problem is solved is by using screws that have a tiny slit cut into them. You should be able to see that there's a slot cut down the whole length of the screw. You can also see it from the top here. And this slot enables air molecules to get out of the hole, which would not be possible without it. And both screws have this slot cut into them. So that's the way this problem is solved. And of course, as soon as I have the optical slit, it will be mounted between those two discs right here. So this is the whole assembly without the optical slit. As I've already mentioned, I need to heat this end here to around 200 degrees Celsius. And you may ask how I plan to do that. And the answer is that I thought about different methods. I thought about using one of those heating clamps that is used for injection molding machines, DIY injection molding machines. But in the end, I settled with these heating cartridges. They are meant for 3D printers. They are 24 volts, 50 watts, I think. Yes. And I have these 6mm holes drilled here in the back. And they fit in there. And I have 3 holes because I have 3 of those heating cartridges. There is a tiny amount of play right here, otherwise I wouldn't be able to push them in. I probably will be using some high temperature thermal compound to get a better heat transfer from the heating cartridge to my atomic beam furnace. And there's also a 6mm hole a M6 threaded hole here on the top, and that is meant to accept a K-type thermocouple which screws in here, which helps me monitor the temperature of the atomic beam furnace. To power and control the thermal cartridges, I have built this box right here. It basically consists of a cheap PID controller from Amazon. It is a Rex C100. It is the same one I used for the temperature controller for my kiln. And I will show you quickly what's inside. Here you can see the PID controller, which I can use to set a certain temperature, in this case 200 degrees Celsius. And here is the solid state relay. These solid state relays are very prone to failure, as far as I heard, at least the cheap ones. I never had any problems with the one in the temperature controller for my kiln, but yeah, you should have an eye on them to make sure that they don't fail, because I heard if they fail in the closed position, so your device is powered all the time. And the solid state relay here basically just switches the 24 volts to the heating cartridges on and off, depending on the temperature my K-type thermocouple senses and provides for the PID controller. And this controller box just fits right in between the aluminum extrusions, just like that. It gets screwed on from the back here with some T-nuts, which sit in these slots, and then I can use it to control the temperature of the atomic beam furnace. To power this device and also the heating cartridges, I'm using a 24 volt 16 amperes 15 amperes switching power supply, and I built a mounting bracket out of aluminum which mounts on this side right here. To actually connect the heating cartridges to the PID controller, I plan on using some barrel jacks, and I think I should have enough left. Yeah, perfect. 1, 2, 3. I am now going to solder these barrel jacks to the heating cartridges, and I will leave the cable of the heating cartridges as long as possible because I don't know yet where exactly all the components will be placed, and it would be a shame if I didn't have enough cable left in the end. Some of you might remember that my soldering station from ERSA gave up while soldering for my vacuum gauge controller project. And I just wanted to say that I think it's very cool. I wrote them an email, sent them my defective station, and they tried to repair it. Apparently it didn't work. They just sent me a new one free of charge. So I think that's very cool from ERSA, and it shows that there is a upside in buying something more expensive from a good brand. I'm also going to connect the thermocouple via a barrel jack. And yes, I know it's not optimal to solder thermocouples or in general connect them to a dissimilar metal, because the Seebeck effect will also act upon not only upon the different metals connected at the thermocouple, but any other dissimilar metals in the connection towards the actual measuring device. But as long as there's no temperature gradient along this connection, we won't get a false reading. And at temperatures of this range, 200 degrees Celsius, I don't think the effect will be significant. Well, solder doesn't even stick to the metal these wires are made of, so I'm just going to crimp them. Let's plug it in and see if we get some magic smoke. So far so good.
When using the PID controller, it did not work properly. I measured the output and the voltage controlling the relay, but I had problems finding the issue.
Okay, I think I found the issue. I was just talking about those cheap solid-state relays from China, and it looks like mine was faulty at arrival. It doesn't even open, and before it was closed for some time, so my atomic beam furnace heated to I think 250 degrees Celsius, even though the PID controller should have shut off. And right now the relay doesn't work at all, so at least we know that the heating cartridges are powerful enough, or even way too powerful for the atomic beam furnace. I'm just going to have to order a new solid-state relay. Okay, never mind, the relay is okay. I'm just an idiot. This relay is meant for AC, as indicated by this AC right here. So I just bought a relay suitable to switch DC, and I'm going to install this one instead. So I'm very sorry for bashing cheap Chinese relays. I switched on the PID controller, and you can already hear by the fan of the power supply that the heating cartridges are not heating up, which is also indicated by the temperature right here and right here. I'm now going to adjust the set point to, let's say, 50 degrees Celsius, or 54, yeah, 50 degrees Celsius, and the relay opened, or it is pulsing. You can hear it by the fan of the power supply, and we see at both temperature sensors that the atomic beam furnace is heating up. As you can see, the temperature differs a little bit between the thermocouple of the PID controller and inside the atomic beam furnace, but it's 1 degree Celsius, so it's not like that matters. I'm pretty impressed how accurate the temperature control is, because there's quite a lot of thermal mass here, and you have to consider that after dumping the heat in the metal, it takes some time before it reaches the thermocouple. So considering this, I'm pretty satisfied. I will now try to heat it up to 200 degrees Celsius and see how it works. The temperature is around 7 degrees lower inside the chamber, but yeah, that's not a huge problem. I can just adjust it right here if I know that there's a difference, and I'm pretty satisfied with this result. It looks like the temperature at the sealing surface of the O-ring is around 165, 166 degrees Celsius. I really hope that by using Biton O-rings, which should be good up to 200 degrees Celsius, this won't be a problem, but we will see later when I test the atomic beam furnace in another video. Even though everything would be ready to install, I'm not going to do it right now, because I firstly want to use an electrical distribution box at the back of this setup, just so that I don't have 3 or 4 power cables running to the socket. And I'm going to do that when everything else is going to be installed, and when I talked about my swivel unit right here. This is going to be talked about in a later video. And because another great guy, Berghauser, made these 3 parts for me. He also made one crucial part for the detector for me, so that's what you're going to see in another video. But he made these ones for me, which will replace this 3D printed clamp on top here, because if you see my other videos, you know that I can't bake out the system because this one is out of PLA and it will melt. So by using these steel brackets, or I think these are aluminum and this is steel, I can bake out the system no problem. So this is what I'm going to install now. And again, thank you very much to Berghauser who made these for me. First, let me take off the molecular pump. And why is there no cap on there? Way better. Let's also put a cap on there. New faceplate, or baseplate, old baseplate. Doesn't that look gorgeous? Again, thank you very much for machining this part for me. And again, thank you for machining to Silver Oranges for machining the atomic beam furnace for me. This was it for today's video. I really hope you enjoyed it. It is one of my slower videos, let's call it that. And in the next video, I'm going to talk about the detector and show you how I build it. And after that, hopefully, we will be able to detect our first potassium atoms inside this high vacuum chamber. I really want to thank my patrons from the bottom of my heart for their financial support. And if you are interested in supporting me and projects like this, consider joining my Patreon. You will find the link in the description. Other than that, thank you a lot for watching.